trying to get this so that it expands. There we go. All right, I think we're up and running. Oops, I just put the finger on the lens. That's not a good thing. I hope it didn't blur things. Do I have a, yeah, I'll use the shirt. Let me wash the lens. All right, you had to put up with a little extra time here before I got this video started. Hopefully that's lens is clean enough so we don't have a blur. All right, so this is going to be a little discussion about imaginaries. We're going to get up to speed on some pretty typical type skill problems that we do with reference to these types of numbers. First off, what are imaginary numbers? That's a good question. Descartes, Gauss, Euler, Cauchy, a lot of famous mathematicians have had different things to say about what we're going to talk about. Maybe 10 years ago, I had a little different look at what I thought I've been working with all these years. Imaginary axis in textbooks tends to come out from the board as a third coordinate plane. I don't see it that way. Solving a problem like x squared plus 9 equals 0, for the longest time, mathematicians would just say no real number gets that job done. Hence, get the marker, you make something up. And what we're making up is no different than any other number, at least according to Gauss. He doesn't like the name imaginaries. Descartes gave it imaginaries in the 1600s. So how would we solve x squared plus 9 equals 0? Well, 0 is the x-axis. So when does this calculation hit this altitude? Never. And that's why for many years, people said no real answer. But if you imagine that the graph went in the other direction, well, then yes, we would have points of intersection. And so it's that imaginary process. What do we need to do? We need to square some distance. And if you squared 3 units, you would have gone up to a height of 18. You would have gone up 9, but we really need to go down 9. And that would be an imaginary process. That's one way to think of it. Mathematicians were stymied. How do you find a number times itself that gives you -1? Well, 1 times 1 certainly doesn't. -1 times -1 certainly doesn't. What does work? Well, what works is the square root of -1 times the square root of -1. That's what works. What will work better is making sure I have an eraser here. Let me grab one. I don't expect to be talking more than 20 minutes here. Hopefully that's plenty. So square root of -1 has been given the letter I to have the same meaning. Now, which is easier to write? Obviously that. So if you take I and multiply it times I, then you get I squared, and that's what we're going to say equals -1. Just making it up. Okay? But it does some nice things. So this would be positive 3i, this would be negative 3i, and so when I plug that in, plus or minus 3i, and I square it, and I add 9, let's see what we get. Doesn't matter, plus or minus 3, 3 squared is 9, I squared, plus 9. So what does I squared do? It changes the sign of the number in front of it. And if I change positive 9, if I change the sign, I get -9 plus 9 equals 0. All right, so I squared acts as a sign changer. And a sign changer in a parabola that's cup shape up, a sign change makes it cup shape down, and then that will intersect at a height of 0. So there are really, I hope this erases a little better. I threw some liquid on there. I gotta get those washcloths back so that we can do this more easily. So there's 3 types of problems that we generally work with. That's one, solving a problem like 2x squared plus 24 equals 0. We can use inverse operations. 2x squared equals 24. X squared equals 12. X equals plus minus the square root of, oh boy, I already blew that, -24, right? -12 plus minus the square root of -12. Okay, late in the day, I make these types of mistakes I hope I'm still recording here. Looks like the last class just popped up. Yeah, still recording. Just went off my screen. So whenever you see a negative inside a square root, what I'm hoping that you'll learn this term is you erase it and you put the letter I after it. Why? Because the square root of negative 12 could have been written as the square root of 12 times the square root of negative 1. And we said it's easier to write square root of negative 1 as I. So simply take the minus out and write I. And so this is equal to plus or minus square root of 12 is the square root of 4 times the square root of 3 times I. I hope you practiced that in your last class. And there's an easier name for the square root of 4. It's 2. Now, why is it helpful to write that? Because I know the square root of 3 is about 1.73. And all I'm doing is doubling it. Gives me a sense of size. Okay, so that's one type of question. 2 more types of questions that we do. Actually 3. We do some binomial squaring. We might do 5 plus 2i squared. That's a fair question for class tests. All right. So 5 squared is 25. The product 5 times 2i is 10i. You remember to double it. And 2i times 2i is 4i squared. And I hope you might know what the number 4i squared is. I squared is a sign changer. So that's going to change positive 4 to negative 4. So 25 plus 20i minus 4. And that our final answer is 21 plus 20i. And that's written in the complex form of a plus bi. That's called a complex number. This is a complex number. It's a little more complicated than the normal numbers. That's the answer to this problem. And we're going to practice that on our worksheets now. Tomorrow's worksheet, I'm going to find one. I'm going to make sure that problem's on there. Okay. So we'll give you a chance to pause the video and do one. You try this one. 4 minus 3i squared. You go ahead, pause the video. I just keep going here. 16 minus 24i. I'm doubling that product. Plus 9i squared. 9i squared is going to change the sign of positive 9 to negative 9. And 16 minus 9 is 7. So there's your final answer for that one. So that's a typical problem just to practice the mechanics of working with I. And I believe I is actually used in electronics. Okay, can't tell you the context, but I know that to be true. All right, so that's one type of problem you're going to do. Another type of problem you're going to do is to simplify something like 5i to the 17th. Well, let's see, 17. Okay, what's an easier way to write that? I put some problems down on the side there. So I'll do this one. Well, we know what I squared is. And I'm going to build this number into that. So I got to get 8 of them. I squared times I squared. That gets me up to 16. One more makes 17. So this is exactly the same thing as this number, but it's just written differently. But the beauty of this is I know what I squared is. It's negative 1. And I know if I do negative 1 8 times, negative 1 times negative 1 times negative 1 times, I get positive 1, just like I squared. I squared is negative 1. I to the third would be I squared. No, let's see, how do I want to do this? I squared to the 1 is negative 1. I squared squared is negative 1 times negative 1, positive 1. I squared to the third is negative 1 times negative 1 times negative 1. That's negative 1. I squared to the fourth is another negative, which makes negative 1 positive 1. Even gets me positive 1, odd gets me negative 1. Even gets me positive 1, odd gets me negative 1. Well, I have an I squared negative 1 to an even number. That's going to get me positive 1. And so this is 5 times positive 1 times I, which is 5i. Now, this type of problem usually takes several days of practice before you can knock it out of the park. But I'll give you another one to try. Let's do 5i to the 40th. We'll do a couple of these, 3 or 4 maybe. So you pause the video, you try it. All right, so what is another way of writing I to the 40th? 5i squared 20 times. That's 5 times -1, 20 times. I don't want to have to do 5 times -1 times -1 times -1 times -1 times -1, 20 times. -5, +5, -5, +5, negative, just alternates, right? And whenever it's even, it changes to +1. So this is 5 times 1. My answer to 5i to the 40th, +5. That's an easier way of saying that number. Let's do 5i to the 43rd. And then we'll start banging them out in class 2 or 3 every day. Hey, how would I write 5i to the 43rd? Well, it's 5i squared. 21 times gets me up to 42. Times I gets me, that's to the 1, right? 42 and 1, 43. I'll write the 1 here. You won't have to down the road. That's a dot. Okay, times. So this is 5 -1, 21 times I. If I do this 21 times, -1 times -1 times -1, an odd number keeps it -1. 5 times -1 times I. Answer, -5i, is another way of writing 5i to the 43rd. So we're going to practice that. And the last one is about conjugates. I'm hoping you did this in your last class, but it doesn't sound like you did. So let's do 3 plus 2i, I don't know what I wrote over there, over 5 minus 4i. Okay? Mathematicians do not like to divide by I. It's kind of like thinking about pi. You know, what is pi divided by 2? Okay, 3.14 divided by 2. I have a feel for that. Do I have a feel for 2 over pi? Not the same, right? I don't have a feel for 3.14 into the number 2. It bleeds into it. So we don't like having irrational numbers or imaginaries in the denominator. Again, do you have a feeling for the letter I divided by 2? Yeah, sounds reasonable. How about 2 divided by I? I don't have the same feel. So we like to get imaginaries out of the denominator. And the way we do that is with a conjugate. And conjugates are really the other half of complete, a squared minus b squared is a plus b, a minus b. What's the conjugate of a plus b? A minus b. So what's the conjugate of 5 minus 4i? 5 plus 4i. Now, if I multiply the denominator by that, I better multiply the numerator by the same number. Otherwise, the size of the fraction has changed. We can do the FOILing up here. So 3 times 5, why don't I do it here? 15, 3 times 5, 3 times 4i, 12i, 2i times 5, 10i, and 2 times 4 is 8. And I times I is I squared. Denominator, 5 times 5, 25. 5 times 4i, 20i, minus 4i times 5, minus 20i. A minus times a positive is a minus 16, and I times I squared. Okay. Notice those two terms cancel in the denominator, which means the next time I do a conjugate, I'm not writing them anymore. They always cancel out, that a squared minus b squared factoring process, right? These always cancel. So we're not going to write it the next time. We're just going to look at 5 times 5, 25. We know the middle terms cancel. So we do minus 4i times positive 4i minus 16i squared. What does I squared do? Changes negative 16 to positive 16, which gives us 41. What does I squared do to positive 8? It turns it into negative 8. And 15 minus 8 is 7. And 12 plus 10 is 22. Okay, so the video is getting a little longer than I wanted, so I'm not going to do another one. We'll do it in class. You're looking at it tonight. Replay this. That's your answer for that one. Okay, no more i's in the denominator. Okay, now the last one was actually the first one we did. I just want to do it again. Okay, so when would something like 2x minus 3 squared plus 8 equal 0? Well, this graph has a cup shape up, 3 comma 8. 0 is below it. We've got imaginary roots. So what would I do? I'd subtract 8. Bang, gone. Just saving some time here. I divide by 2. Negative 4, gone. I do the plus minus square root. Gone. I take the negative. I put it out. I take the square root of 4. I make it a 2. And then negative 3 comes to the other side, becomes positive 3. 3 plus or minus 2i. There's your answers to that. Now let's go back to what we had here a second ago. So we had squaring, we had plus 8, and we had a 2. So I'm going to put my answers in. I'm going to do 2 times 3 plus or minus 2i. That's what I'm replacing x with. Then I'm subtracting 3, I'm squaring, and I'm adding 8. I want to look at what I get here. What happens to the 3's? They cancel. What's 2i positive from negative 2 squared is 4, 4i squared. So this becomes 4i squared. What's 2 times 4i squared? 8i squared. What's I squared do to positive 8? It makes it negative 8. And what's negative 8 plus 8? 0. Okay, so it's giving you a feel for just the process, you know, what I have to do to the squaring process to make it change down 8 units. And I've got to do this in that problem. All right, so those are the problems we're gonna practice to get better at skillfully, so that we can work with the imaginary situations for roots. And we'll, oops, my battery's going to die. Goodbye.